I am Saroj Vishwas, gold medalist, first rank holder of 1994 batch in engineering stream of all the colleges affiliated to University of Mysore during that period. A BE in civil engineering from National Institute of Engineering Mysore, a MTech in structural engineering from Indian Institute of Technology, Delhi, that is IIT Delhi, a Sun certified Java programmer, Sun Microsystem USA. I have more than 25 years of professional experience in designing building structures and allied subsidiaries. I invite you all to learn with me how to design building structures using commercially available structural softwares with the help of some manual computation as and when needed. This is how the CAD drawing would look like when the base plate details are translated to a CAD drawing from the structural GA data, base plate data, etc. provided by the structural engineer. Now the next step would be to design the foundation for this structure. Now usually in case of a PV firm, they do not design the foundation part, substructure part, they outsource it to some consultant. But to be a good structural engineer, to become a good structural engineer, one should know how to design RCC structure as well. For example, if you design a composite structure and you are designing simply supported beam, which is a composite beam. Now the design of shear stud will depends how much force is being transferred or how much strength is being contributed by the equivalent concrete flange of the beam. Now for this, the reinforcement in the concrete deck slab is also required to be designed. Now it is really difficult for an RCC engineer to design this reinforcement without knowing how much contribution is being made by this concrete part to the strength of the steel part. So to become a fine structural engineer, one should know how to design RCC as well. Now this is our base plate detail. Now we'll first get the location of the walls. So for that, let us take this base plate detail somewhere else. CO copies the command for AutoCAD, drag to select, enter, then take a base point and place it somewhere here. We have the architecture plan here already taken from the architectural drawing and pasted over these drawings. So let us take this wall, brick wall, copy, select this block of brick work. If it is not a block, you should make it a block. Now we should choose a reference point which we have. So I can copy CUP, copy, select the wall, then let us take this intersection as a base point. Now let us place it here at this intersection at the destination point. Now we have this wall. Usually a base plate should have at least 25 minimum concrete edges outside the base plate, but for good workability one should have 75 mm of edges available, concrete edges available from the edge of the base plate. In PV structures I have seen the PV designers are taking to that extent of 150 mm, which is at times really not required. They just do it because to ace their anchor bolt fixing part, but economy doesn't remain consideration for them. So as a structural engineer, we should not do that. We should always try to provide as much as possible an economic solution. So we'll take a offset of 75 mm around this base plate. So let us take this offset 75 mm around this base plate. O is the command, enter, then enter the distance 75 mm, then select this boundary, enter. This base plate has been made as a block, so we need to explode it. EXPL, click inside, then type EXPL, then select the object. We should explode everything, so EXPL and select everything and enter. So now our objects are exploded, so individually we can work. So we have to go for a offset of 75 mm, offset 75 mm, okay. Then for every one, let us go for 75 mm offset for every wire. Now this part, you see, this part the draft manual detailer has been actually made as a line, not a rectangle, for this base plate. So the outer offset lines are not joined, so we can use fillet command to do it. So F is the command, then type R, because at times R could be different, then type 0, then select the objects, so it is joined, then enter again, then select objects, joined, joined, joined. So we have this base plate. Now we have a brick wall all around the building as shown here. So our plain beam must support this brick wall. So let us first draw this brick walls, draw this plain beam. It is better to always use Excel command to draw the lines, because they always remain straight. Excel V I am taking first, Excel, then enter, then V, enter. So we have this command Excel. We can change the color, CUL color, Now let us take yellow color. Okay, then XL V. So I have a offset here. I should have a plain beam here. I should have a plain beam here, and I should have a plain beam here. Then again XL H. So I need to have a plain beam here. I need to have a plain beam here as well. I need to have a plain beam here. I need to have a plain beam here. Now let us trim all of this. Trim, TRIM, trim command, then enter. Select by dragging in opposite direction from right bottom corner towards left top corner. So everything will be selected. Then enter. Then select these parts. So many parts are also left. We should delete them. Now I don't need this brick wall as of now, so I delete it. Select it and press delete command. So I have the location of brick walls. So let us fillet them. F fillet. Select this. Select this. It is filleted. Then select this. Select this. Then select this. Select this. This and then this. And this. And then this. Again fillet this. Fillet. We have to select this one and the one which we want to keep. So our plain beam is there. You can see the steel line. It is outside the brick wall that has been drawn by our detailer. So now we need to increase this pedestal size. So what do you do for this? You draw a line, drop, draw a line here, drop. Similarly draw a line here, drop here. Similarly draw a line here, drop here. Similarly at all places. Now having drawn this, we should now determine what should our actual pedestal size should be. So let us change the color. COL color, make it white. Okay. Then let us draw a rectangle by pulling like this. So this is our first pedestal, rec. Second pedestal, rec. Third pedestal, rec. Fourth pedestal. Similarly, we should draw it all the other places. The next, having drawn all the pedestals, the next step is to locate the CG of these pedestals. So for that, we need to draw some lines. So let us first make the pedestal layer as current layer. So go to the layer, set current, color, by layer, then line. So this is our line, this is the other line. So this is the CG of the pedestal at the corner. So now we should measure the distance in this direction. So this is 40 mm here. Let's see it. The CG is 40 mm outside the CG of the column in horizontal direction, and then DLI again this. So DLI, this is the CG column and this is the CG of the pedestal. So this is 62 mm outside the column CG line. Again, let us go to this. So the CG is CG of the pedestal is eccentric with respect to the column in one direction only. So let us first draw the lines to look at the CG of the pedestal. So now let us measure the distance. This way we should locate the CG of distance between the CG of the columns and the CG of the pedestal at all locations, and thereafter only we should proceed for STAAD Pro modeling of foundation. Here we have located the CG of the other side column also. So for these columns the CG will be mirrored to this, and this will have a different CG, and one column here. For this column the CG of the pedestal is 75 mm outward from the CG of the MS column. So now let us go to the STAAD Pro file. This is our STAAD Pro file. Now we have to first find out the reaction for every columns. So this is node number 1. Let us tool, cut section, exit plane, node number 1. We don't record this node, so select by inverse node selection. We use selected object only, so we have only the required nodes for our foundation design. Now mode post processing apply. You have to take reaction for all the primary load cases. So report, support reaction, loading, EQX. So this is our load case 1. Let us open Excel file. So this is one of our Excel file. So what we do, we paste this reaction for load cases. Similarly for all other load cases, primary load cases. So these are our reactions for all the load cases. Load case number 1, 2, 3, 4. Note that we have not taken the response spectrum load cases, primary load cases. Taking only static load cases is adequate, because the response spectrum will give only results in positive direction. It will not give results with negative signs. So wherever there is a uplift, we need a negative sign. So it is better to design the footing with reaction obtained from static earthquake cases. So we have all this. Now these are the reactions. So what does this means? This means these are the load which will be applied on the top of the pedestal. So what should be the load that should be applied? So let us do one thing. How we apply load on in STAAD? We should first write load case 1, then joint load, paste. Here should be the joint load, then this should be the node number, then this should be the fx. Fx is equal to minus 1 into, so we can do one thing. We'll insert sub columns, insert, 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 then again insert. So this is our fx, this is our fy, this is our fz, this is our mx, this is our my, this is our mz. So what we do now, we just pull it down. So this is our load case number 1 that will be applied using the editor on our foundation model. So just take it, copy it, paste it here. So this is load case number 2. Change it to load case number 2. So similarly, we should find the applied load on the top of the pedestal using Excel file for all the primary load cases. So this is the all load cases. We will have load case 28, 21 to 28 is our wind load cases. Then load case 11 was our dead load for the floor. Then load case 12 was the wall loads, and then load case 14 was the dead load, live load. So now, having this data, we should also have the data what is the node numbers. So shift S will put up the support icon, then shift K, then shift N. Now these are the node number. Take a snipping tool, new snip, edit, copy, then paste on our Excel sheet. Now next is, what are these primary load cases? That the information should be also there. So go to load and definition, load case detail. So our primary load cases which are provided is this. Again go to the snipping tool, cut it, edit. We can take paint, paste it here. We don't require this 5, 6, 7, 8, 9. Just delete it using the cropping tool of the notepad. Then cut it from here. Then paste on the node. When you paste it from the paint, it usually goes to the top. So cut, then paste here. So we know what are our primary load cases, we know the node numbers. The next step is to form the foundation model. So let us go to the start file, new, space, file name is foundation model for hypothetical building. Unit meter kilometer. Next, finish. Let us see where has been it saved. We should save in a appropriate mode, appropriate place. You are saving in the folder of hypothetical model building start folder. So let us save. Now go to edit. Go to edit, exit plane. Okay, there is a node that is indicated by mistake. So let us go to the architecture plan, base plate layout. We have this base plate layout. The distances are 6 meter, 6 meter, 4 meter, 4 meter. So edit, this will be 12 and this will be again 12. Okay, snap node beam 12 meter, snap node beam 12 meter, insert node, 3 nodes, insert node, add midpoint, copy, we can now close this one, copy, paste reference point. Now see, here the node numbers are different from what we require. Here 1, 9, 3, 5, 31, 7. This is the way actually a PV engineer provides the reactions to a RCC designer. But all said and done, I would always prefer the structural engineer should become a complete structural engineer. He should know both RCC and steel building design if he is a building design structural engineer. And anything other than that, if he can do, always better. But at least both the things should be known to him for a structural engineer. Then only we can call him a good or fine structural engineer. So we have to renumber this load. For that we have to first go to the geometry, renumber nodes. Okay, put it here 1001, X, Y, Z, anything you can do, accept. Now this nodes numbers have been renumbered as 1000. So now our first 3 nodes are from our Explorer 193. So tool, geometry renumber nodes. First one is 1. Yes, take X coordinate. So see, this has become 1. Then again geometry, 3 number node x, this was 9 except, then the third one was 3 geometry, 3 number nodes 3. So this is the way you should renumber all the nodes so that it matches with the node number given in the reactions. Actually there are 3 such groups, so I have inserted these have become 3 meter, this should have been 4 meter. So let us delete, readjust them. Now the grid to grid dimensions are same as it is there in our STAAD model. So let us proceed for renumbering other nodes as well. Now we have renumbered all the nodes. Let us check with our Excel file. So this is 193, 530 on 7, 530 on 7, 632 8, 632 8, 2, 10 and 4. So this is okay. So let us save it. Yes. Save the Excel file. Now let us save our model also. Save. Now our foundation, the architectural drawing doesn't give difference with respect to the NGL, so we will assume some difference with respect to NGL. Let us assume that plinth level is 600 mm above the natural ground level. So with 50 mm finish, the top of the concrete shall be at 550 mm. So if, and since we do not have a bearing capacity report here, soil investigation report here, so we can assume that we have been given a set bearing capacity at a depth of 1.5 meter below the natural ground level. So 1.5 into 0.55 is 2.05. So let us take all this we should take all these points to 2.05 below this level. Now before doing that, we know our pedestal CG eccentricity with respect to the column CG. So we should first locate those nodes. So let us go to the AutoCAD file. So see the side columns are 27 outside, 27 mm outside the grid line or CG line of the columns. So let us move, copy nodes, copy, paste node, minus 0.027. Okay. So this is really very less. So here also copy, paste node, 0.027. In the corner one, the first one is 40 mm. And this one is also 40 mm. So let us copy, paste node, minus 0.04. This one is 51 mm and this one is 27 mm. So this should be also 40 mm. Copy, paste node 0.040. Now this is again outside 27 and this is outside by 51 mm. So move them, move minus 0.027, okay, and here copy, paste node minus 0.052, 0.051, okay, minus 0.051. Now this two is 62 mm and this is 75 mm. So move these two node, move in Z direction 0.062 and move this, copy, paste, .075. So we have our pedestal locations. So now let us select this node only. Go to geometry, translation, repeat y minus 2.05, that is 1.5 plus 0.55 is equal to 2.05. Link step, okay. So these are our pedestal CG. So now next thing we need to do is to connect this model. Paste reference point, paste it here, copy, paste it here, copy, take the reference point and paste it here, copy, take a reference point and paste it here. So now let us cut the section at this point. 38, tool, cut section, exit plane 38. So what will you do now? Geometry, add beam. We shall drop a perpendicular from here, then from here, then at this corner as well, from here. Note this is our column and this is our CG, column CG, and this is our pedestal CG. Paste here, paste here. Now let us delete all this. nodes. Before deleting that, let us connect these nodes as well. This, 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 this. So now let us delete these beams. We are left with one of this. Okay, delete it. Yes. So we have our model here now. View whole structure. Now let us see how much away is the plane beam center from the column center. So DLI, this is 300 mm away from the column center, the center line of our brick wall. So let us copy, paste, minus 0.3, and let us delete this beam. Then copy, paste beam, plus 0.3. Let us delete this beam as well. Now how far is this center line of this brick wall? DLI 273, and on the top side line DLI 202. So copy, paste beam, minus 0.202, delete this beam, copy, paste beam, minus point, what was our distance? This was 273 from the CG line of the column. So 0.273. So delete this one. So again we go to exit plane, 70 tool, cut section, exit plane, 70. Now let us connect. Now let us do one thing, copy, paste beam reference point here, copy, paste beam reference point here, copy, paste beam reference point here, copy,
page beam here, copy page beam here, here, copy page beam reference point here and here. So geometry intersect, so we don't need this. So let us first join this geometry, merge selected node, selected beam, merge selected beam, and here also geometry, merge, merge. Look, we are merging only the corner members, not the in between members. If you took many members in between, it might results like if I select this also, so it could result catastrophic things. So you should be careful while merging beams. Geometry, merge, merge. Okay, then geometry, merge, merge. Now what will you do? We shall drop perpendicular geometry, add beam from our pedestal center. This is our pedestal center. This is a perpendicular. This will connect. This is perpendicular. This is a perpendicular. This is the perpendicular. This we can join. These two we can join. And here again, perpendicular from pedestal center, perpendicular pedestal center, perpendicular pedestal center. Join pedestal center. Here you join the pedestal center, then here you draw perpendicular on the pedestal center. So view whole structure. We have some pedestal here also. Their centers matches. So geometry, translation repeat, y minus 2.05, link step. Okay. So I would like to have a single model, so I am connecting it here, and I will provide a zero density for this member, and geometry, command member specification, release, start MIMZ, command member specification, release, and MIMZ. So we are assigning a member, a dummy member, just to have a single structure when we take with respect to the tools. So this is again. Now for example, if you go to tool, check multiple structure, we have only one structure. Now if I delete one of these two, now just check tool, multiple structure. Now see, you can see two structures. So to avoid that error, we are providing this member. So let us undo it, Control Z, Control Z. Now this is our plane beam, and these all will be our plane beam, and these are our pedestal. Now we need to know the pedestal sizes. Not while drawing, we should draw the pedestals in a different layer so that we can copy it outside and measure the distances. I had already drawn it in a different layer, so for that I will do one thing, lay ISO to isolate a layer. I have isolated it. Now copy, I don't need this. I do not need all these dimensions. Now here we have 1, 2, 3, 4, probably 5 types of pedestal PLI. This is 580 PLI. 750. Similarly, in this way, we should dimension all the pedestals. So you can see we have 6 types of pedestals. These are mirrors of this, and this is different. This one. Here 3 types, and here 1, 2, 3 types. So 6 types of pedestals. So let us now note down this and define these members. So we'll, having noted down the pedestal sizes, we will define this pedestal. So rectangular. First is our 0.75 by 0.580. Add 0.720 by 532. Add. Similarly, we should define all the others pedestal. So we have defined all the pedestal sizes. Note, I am keeping standard that I would keep the getter depth as YD. So these two ones were this pedestal, then this one was this, second one was this, third one was this, 4, 1, 2, 3, 4. Fourth one was this, fifth one was this corners one, then sixth one was this. Now if you look at the 3D view, now see the orientation of this we need to change. So let us go create 90-degree beta angle. Okay, select this and select this beta angle, assign. On member inspection, release, this release are removed, assign. So if you look at the view here, now our pedestals are okay. So the next thing is we'll define the premium sizes. For a 6 meter depth, 0.450 should be sufficient. 0.45 by 0.23 if required, we'll change it later. Add. So define this. We assign to this. This is our pedestal. Now I will define the member connecting to the CG of the column from the CG of the pedestal and from the CG of the pedestal to the central line of the beam. Now there are two ways to define it. One is to define a rigid member where we increase the elasticity of the material by 10 times or 100 times, so it become very rigid. But I prefer to define it other way. So it is almost, it's because nothing is infinitely rigid, so it's provide the same kind of results which we want. So I'll define a member of width point, say 0.35 and depth same as the column depth, 2.05. But would like to see this member at the top. So what I will do, I will take the help of user defined table tool, create user table, new table, channel, okay, add new property. So we'll define something like this, simple member by 0.35 by 0.35. So let us take the help of Excel file. So these will be our coordinates, and this is BD cube by 12 with depth as 0.35, that is 2.5 to the power and its Sx will be 0.25 divided by 2.05 divided by 2 m cube. So let us copy it, Control V. So we have this compute section properties. So we should also fill this. Let us fill it as 0.3535 itself. So let us define it's a rigid member, and then we have to change this IZ and SZ. So we have the IZ as 0.25, copy, Control V, and HZ as 0.2, Control C, Control V. Okay, we have this property, save table. So let us go to the user table, upt add. Now select by missing property. So this we do not need. Control Z. Upt rigid add, select by missing property, assign. So all this member has been assigned as a rigid member. Now let us go back to the editor. Let us go to the editor. We have to define a concrete member with zero density. Control C, Control V. So this is concrete. Zero den, save. So we have zero density member, so we will shoot 0.0001, not providing exactly zero, shows exactly zero so as to avoid numerical instability. So see, this has become basically R3. This is R3. and I should have defined this as a concrete member. So concrete UPT assign. Now I delete this. Now I define a dummy member, say 0.23 by 0.23 with concrete as concrete zero density. This we define as a zero density. Now let us assign support to this pedestal. Create fixed support. Footings are 99% cases it is fixed unless it is a very soft soil. Footing cannot behave as a hinge soil, although it might behave as a partially fixed footing, but for design purpose we can take footing as fixed as long as the permissible pressure does not exist, the load does not create settlement greater than the allowable settlement in foundation of the design. So bearing capacity is given with respect to the minimum of allowable settlement or shear failure of the soil. So if you maintain the bearing capacity within allowable SBC, so our footing will not be subjected to settlement greater than the permissible settlement. So having defined this, now it is time to transfer our load. So let us open that Excel file. Our Excel file was here. Open reactions.excel file. This is our reactions. This is our reactions. So let us copy it. Copy. Then go to the editor, save. Below support, let us define this load, save. So you can see the loads has been assigned. To the, let us go to the load case 11. So these are all the loads that is being subjected. So our load cases is load has been applied. So the next thing is we have to define a self weight. Here we'll go to the editor and self weight, and we have to add a dead load of the brick load on the brick also with 0.1 meter of brick masonry height of 230 plus plaster usually gives a 5 kN per meter of weight per running meter. So 5 into 0.9, our wall height is 0.9 meters, so 4.5. So let us add a load of 4.5. Select by specification, property name. This is our plain beam. Assign. This property was not defined properly. Shift X. So this should have been R3. Assign. Okay. So let us now give a run. Before giving a run, we have to write perform analysis, and also we have to add the self weight in the dead load. So this was our dead load. So load case 11 was order self weight SELF self weight y is equal to -1 and here our perform analysis. Now let us give a run. There are some warning in the start file. So what I did, I deleted all the properties and assigned them again, because I did not want that start should give warning that last values properties has been duplicated and last values has been used. This kind of warnings I did not want, so I deleted all the sections and redefined them again. So now let us give a run to this. So there is 0 warning. Now if we see the movements, so you can see movements, MX, MY, everything is there. See, these movements have been acting similar to a portal with movement distribution from top, and these movements are transferred out of cantilevers. So with this we can define the load combinations and then go for designing of the pedestals and footing. In next sections we shall define the load combinations and design the pedestals and pedestal reinforcement. So this ends the first section of design of footings.